So we've established what a buffer is. It's a weak acid and its conjugate base, or of course, a weak base and its conjugate acid. And it also resists the change in pH. Well, how is it that that happens? Okay, so buffering, how it works. So we remember that our buffer contains both HA and A minus. Both of those have to be present in appreciable amounts. And so now if we think about this, we can now add strong acid or strong base to this acid buffer. And either way, whether we add strong acid or strong base to an acid buffer, it's still going to resist a change in pH. Okay, so for example, when strong acid or strong base are added to buffers, these reactions go to completion. So I demonstrated that in the previous video, right? So for example, if I add strong base to a buffer, it's going to react with the weak acid, just as we showed with that previous problem, and it's going to make more A minus and some H2O. Okay. However, if I were to add strong acid to the same buffer, doesn't matter that it's a weak acid buffer. I can add acid to an acid buffer, and it's still going to resist that change in pH because now the strong acid is going to react with the conjugate base of that buffer and then go on to produce more HA. So you can see either way, in either one of these scenarios, we still have HA and A minus present. So when it comes to buffering, it's really all about the ratio of HA and A minus that's important. So in other words, we want to have comparable amounts of both in our buffer to really get that strong buffering effect. Okay. So now this is the point where I'm going to introduce a new way to calculate pH of these buffering solutions where we don't need to use a rice table. So everybody jump up and cheer. Let's see. Oh, I should have had this thing ready. Oh, weak sauce on the volume. So no more rice tables, and we'll see why. So here is our weak acid equilibria. HA is in equilibrium with H plus and A minus. We know we can write the Ka as H plus times A minus divided by HA. And if I rearrange this algebraically, so I'll just say rearrange, then we can get this equation for H plus. H plus equals Ka times HA divided by A minus. So all I did was multiply both sides by HA and multiply both sides by, or divide both sides by A minus. And we get to this expression. And now remember, it's the negative log of H plus that we want to get the pH, right? So now if I take the negative log of both sides, let's see what happens. So I get negative log of H plus, and now I get negative log of Ka times HA all over A minus, okay? Well, we know what the negative log of H plus is. That's just simply called pH. And now remember, when we have these log rules, when we have an addition, when we have a multiplication inside a log, it becomes an addition. So now that means we have the negative log of Ka, and then that's going to be minus the log of HA over A minus, okay? And so I can rewrite that now as the following. I can say pH equals, and look, we know that the negative log of Ka is just simply the pKa, and I'm going to switch the order of this. This is just done as a matter of historical context. So remember, if I switch the way, the order in which this is divided, it changes the sign. So I can say plus log, and then now that's going to be A minus over HA. And to be honest, it doesn't really matter that we did that, but this is how this equation is used. And we can see here, this is a really famous equation. It's called the Henderson-Hasselbalch equation. pH equals pKa plus log of base over acid. And so specifically, we remember that that's the conjugate base. But all the same, if we were doing a base buffer, we could readjust this equation for that, okay? And so here, question, when can we use this equation? Buffers only, and when the 5% rule checks out. So if we have a situation in which the 5% rule is not going to work, we can't use this equation. However, in almost all of our bases, and I should say in almost all of our buffers, the 5% rule will most definitely work out. So now we're going to see how easy it is to use this equation instead of having to do a Rice table. Okay, so we've got a calculated pH of a solution that contains 0.75 molar lactic acid, and there we can see the Ka, and 0.25 molar sodium lactate. Now, I understand maybe we aren't familiar with that nomenclature, but remember, acetic acid is the acid, and acetate is its conjugate base. Well, if lactic acid is our acid in question, then its conjugate base is lactate. That's how the nomenclature works, okay? So we can see here quite clearly that the lactic acid is HA, and the sodium lactate, we don't care about the sodium because it's a spectator. That is my conjugate base, my A minus, okay? So that's the only thing we have to get straight to use this equation. And then now we can just plug and chug. pH equals, so we were given a Ka, so we can now just say the negative log of 1.4 times 10 to the minus 4 plus the log. And now it's going to be A minus over HA. And we established that the A minus is 0.25 molar and the HA is 0.75 molar. So now let's calculate that away. So hopefully I don't have any more issues with my calculator like I was earlier. So 1.4 times 10 to the negative 4. And then I'll say log. Okay, that's it. And remember, it's negative log, so that negative cancels. So that's 3.85 for that, plus, and then now let's do the other side. So 0.25 divided by 0.75 equals, and then now I take the log of that. And remember here, there's no negative sign in front of this log. So that negative sign that I get carries through. And so now that's negative 0.48 with the appropriate number of significant digits, okay? And so you can see now when I finish off that math, I can do that in my head. So that means pH is 3.37. So there we go. No Rice table. But we have to remember, buffers only, and when the 5% rule checks out. Okay, what's next here? Okay, very good. That's the end of this video. I'll see you in the next one.